Math 2414, partial fractions 11, example of three-term quadratic factors. I think there's actually two examples I'm going to do here. The second one will be built off of the first one to save time. So let's start with this first one. The integral of x plus 4 over x squared plus 2x plus 5. First, notice that this does meet the degree requirement for integrating by partial fractions. The degree of the denominator, 2, is greater than the degree of the numerator, which is an implied 1. So we can consider using partial fractions. And normally in a situation like this, what we would attempt to do is to factor the denominator. But because the trinomial's terms are all positive, these will all be pluses. And because the constant terms in the linear factors have to multiply to get 5, my only option is 1 times 5. However, if I were to FOIL it, I would get 6x in the middle, not 2x. So it's pretty easy to show that this is prime. By the way, there's another way to show that a quadratic trinomial is prime, and that's to calculate b squared minus 4ac, also called the discriminant inside of the quadratic formula. But if you want to see if a trinomial is prime, a quadratic trinomial is prime, you can check b squared minus 4ac. If b squared minus 4ac, actually this would be a biconditional, so let's get rid of the b squared minus 4ac is perfect square if and only if ax squared plus bx plus c will factor. I'm not going to prove it. I'm just stating it as a fact, and I can prove it. In other words, if you calculate this and it's a perfect square, then your trinomial will factor. Otherwise, it won't. So if you were to calculate b squared minus 4ac on this guy, it would be 2 squared minus 4 times 1 times 5. That's negative 16, which is not a perfect square. And when I say perfect square, I mean perfect square of a real number. And since that's not a perfect square, then our trinomial will factor. Sometimes it's easier to just try to factor it and realize that it won't. But there is a way to test if a trinomial will factor or not. Anyway, so this guy won't factor, which means that we can't split it into two linear factors and attempt a partial fraction decomposition. So we're stuck with it the way it is. So we're not really going to do a partial fraction decomposition. But in a case like this is when you would take this guy and complete the square. And then make a substitution to transform it into an integral that we can do. All right, so I'm just going to quickly remind you how to complete the square on that guy. It's what the previous video was about. But to complete the square on an expression, as opposed to one side of an equation, you leave an empty space for the perfect number that will complete the square. And then if the leading coefficient is 1, which it is, then you simply take half of this and square it. Half of 2 is 1, 1 squared is 1. You need a plus 1 there and balance that plus 1 with a minus 1. Then the new trinomial up front will factor into a perfect square. In this case, it would factor into x plus 1 squared. And then the extra constants after that combine to give a plus 4. So there's a real quick synopsis of how to complete the square in the denominator. Okay, so the denominator becomes x plus 1 squared plus 4 dx. And the purpose of completing the square, honestly, is to get rid of one of the terms. Notice that we only actually see a single x here, whereas over here we saw 2x terms. That's really what the completing the square is intended to do. But at this point, you would make a substitution, and the substitution would be to let u, well, whatever that squared binomial is. So in this case, x plus 1. Then du is equal to dx, so that's always good. The du package is already there, no need to balance it. The u will take the place of the x plus 1, but now we have an issue on the top where we've got an extra x. And when you're doing substitution and you've got a stray x left over, then the standard strategy is to take your substitution and solve it for x. If we did, we would get x equals u minus 1. Then we can replace that x with u minus 1. So if we make all those substitutions, our integral will now become the integral of, on the top we have u minus 1, we still have the plus 4. Then on the bottom we have u squared plus 4. The minus 1 and the plus 4 will combine to make a plus 3. Let's move this to the next page. Now we're at this integral, the integral of u plus 3 over u squared plus 4 du. And when you reach this type of integral, where you have a linear numerator over u squared plus some constant, the strategy is to split it into two fractions, and hence two integrals. The integral of u over u squared plus 4 du, plus the integral of 3 over u squared plus 4. And you handle these integrals differently. The first one you could handle with a substitution, although we can almost bypass the substitution if you're observant. Let me go ahead and write it down. I can't say let u equal, u is already spoken for. So we're going to let w equal u squared plus 4. Then dw equal to 2u du. And to build the dw package, we need a du, which we have, a u, which we have, and a 2, which we don't. But we can put the 2 in there as long as we balance it with a 1/2. So everything double underlined would become the dw. And the denominator would just become w. So this instantly integrates into the natural log of the absolute value of w, but w is holding the place of u squared plus 4. So that. And in all honesty, that absolute value isn't necessary because u squared plus 4 is positive, but we'll leave it there. For the second integral, we don't have to do a substitution because we have an integral rule. The integral rule is the integral of 1 over u squared plus a squared du equal to 1 over a arctangent u over a, and of course plus c, which I don't know if I can fit in that margin. That'll have to do. So if you know this integral rule, and you need to know this integral rule, then this integral is pretty easy. You just have to notice that a is equal to 2, and we've got an extra 3. So we have an extra 3 in front. Then using the rule, we would have times 1 over 2. So 3 times 1/2 is 3/2. An arctangent of u over a, but a is 2. And being the last integral, we need the plus c, but we're not done because this is still in terms of u, and we want it in terms of the original variable, which was x. So now we have to undo the first substitution that said u equals x plus 1. Now, let's go ahead and talk about what would happen here with the u squared plus 4. I already know what's going to happen to that, because let's retrace our steps. The u squared plus 4 is what we got after doing this u substitution. So if we undid the u substitution, it would take us back here. But that was just the completed square version of this guy. So when I put the u plus 1 back in for the, when I put the x plus 1 back in for the u, I'll eventually get back to the original quadratic trinomial that we had. So let's go put that in. 1/2 natural log absolute value x squared plus 2x plus 5. And then over here it's a little bit easier because the u is just sitting on top of a 2. So we could just put the x plus 1 top of the 2, and then we would get our final answer to this problem. I think I want to take just a second to elaborate on that thing that I just said, where if we were to undo the u substitution here by changing the u back to x plus 1, if we FOIL this out, we would get x squared plus 2x plus 1. There's a plus 4, and that's why it would become all that. All right, so there's the first integral I wanted to do on this one, which did, and just to review what happened, did not actually require a partial fraction decomposition because the only factor was an irreducible quadratic. You couldn't get any linear factors. But it did illustrate the completing the square technique and how you would follow through. But I want to show you one more, and this one will actually go fairly quickly once we get the partial fraction decomposition complete. I want to conclude this series of videos with what would arguably be the hardest problem I would give on the homework or a test, but for a full disclaimer, it's not the hardest caliber of partial fraction composition problem out there. Let's say we want to integrate this guy, 4x squared plus 11x plus 19 over x plus 1 times x squared plus 2x plus 5. Now, you'll notice that this is the same irreducible quadratic factor that we had before, so no further factoring of the denominator is going to occur. Plus, notice this satisfies the degree requirement because the degree of the top is a 2, and it's a little stealthier, but the degree of the denominator is 3, found by taking the sum of the degrees of the individual factors. So we can do this by partial fraction decomposition. So let's take this fraction, and in fact, I'm going to get rid of the integral sign of the dx for a second, and let's go ahead and start doing the decomposition on this. The x plus 1 being a linear factor would only need a constant numerator, so we'll say a. And the quadratic factor, x squared plus 2x plus 5, would need a linear numerator, so we'll call that bx plus c. And it is worth reminding you that in algebra speak, linear means degree 1, means highest power, means x to the first. All right, so if we were to do this partial fraction decomposition, we would have to multiply everything by the common denominator, which would be x plus 1 times x squared plus 2x plus 5, and then see what happens. On the first fraction, it's pretty predictable. It would cancel the entire denominator. On the second fraction, the x plus 1 would cancel, leaving an x squared plus 2x plus 5. And on the second fraction, the x squared plus 2x plus 5 would cancel, leaving bx plus c and x plus 1. And now let's begin to find our missing constants a, b, and c by making some choices to what to substitute for x. Remember, the decision here is to try to find numbers that will make some of the factors equal to 0. The quadratic factor won't equal to 0 easily, but the x plus 1 will. So let's start by letting x equal negative 1. Let's see what we would get. If we put negative 1 in the quadratic expression on the left side of the equal sign, we'll get 4 minus 11 plus 19. 4 plus 19 is 23. 23 minus 11 is 12. So we would get 12. If we put negative 1 here, we would get we would get 1 minus 2 plus 5. 1 minus 2 is negative 1 plus 5 is 4. So we would get 4a. And then this would zero out because putting negative 1 in the x plus 1 would give us a factor of 0 over there. So we got 12 is equal to 4a, and this immediately implies that a is equal to 3. Let's put that off to the side because we're going to need that in a little bit. Okay, a equals 3. All right, so that's what happens if we let x equal negative 1. Now let's see what happens. Well, there's no other numbers that will cause any of the factors in the equation to vanish, which will always happen when you have an irreducible quadratic. And I shouldn't say there are no numbers. There are no convenient numbers, no whole numbers or rational numbers. All right, let's see what other number we can pick. Well, 0 is always a good number for x, so let's try that. If we let x equal 0, the left side of the equal sign collapses down to a 19. This quadratic collapses down to a 5, so we get 5a. But we know a is 3, so we'll fix that in a second. Plus, if I put 0 here, I get c. If I put 0 here, I get 1. So 1 times c is c. But we know that a is equal to 3. So 5 times 3 is 15. And just like that, we get c equals 4. All right, well, that was a good choice. We'll put it over here under our list of coefficients, or constants, I should say. And now we got to figure out the b. So let's pick another number for x. Let's try x equals 1. That's a pretty simple number. All right, if we put in x equals 1, let's see what we get. On the left side of the equal sign, we would get 4 plus 11 plus 19. 11 plus 19 is 30, and then plus 4 is 34. We already know a is equal to 3, so let's put that in. If we put 1 here, we'll get 1 plus 2 plus 5, that's 8. We get 3 times 8. Plus, if we put 1 here, we'll get b plus c, but we know c is 4. We'll put b plus 4. And if we put x equals 1 here, we get 2. All right, let's solve this. Let's go ahead and subtract 24 from both sides, since that's what 3 times 8 is equal to. We get 10 equals, and let's go ahead and distribute this. We get 2b plus 8. Yes. And a quick solve will give us b is equal to 1. So solving that for a, b, and c really didn't take as long as I thought. Hooray for that. So what does that get us? Well, it tells us that the partial fraction decomposition is this. 4x squared plus 11x plus 19 over x plus 1 times x squared plus 2x plus 5 is equal to 3 over x plus 1 plus 1x plus 4 over x squared plus 2x plus 5. That's just by putting in the values for a, b, and c. The 1 in front of the x here is not necessary, so let's get rid of it. And let's remember that we're in the middle of doing an integral. So let's recover the integral sign. Now we just need to integrate each of these. The integral of 3 over x plus 1 is easy. It's 3 times the natural log of absolute value of x plus 1. If you need to do a substitution, do it. And this integral is the one that we did in the first example. So there's no need to redo all of that. We just need to borrow its answer. Recall that the answer to that integral was this guy. 1/2 natural log absolute value of x squared plus 2x plus 5 plus 3/2 arctangent x plus 2. And say final answer for this integral, that. And I'll admit that if you had done this integral from scratch, without doing the prior one first, it would have taken more time to attack this second integral. But that's the reason I wanted to do that one first. All right, that concludes this discussion of partial fractions. Again, I want to reiterate that there are much more complicated partial fraction problems, specifically ones whose denominator have repeated quadratic factors. I'm not going to hold you accountable for that, but you need to be aware of